Okay, so this is our CP Biology Enzymes Video Notes Part 1. So you would want to be on the sheet that says Enzyme Guided Notes. We're going to go through Part 1, which is looking at graphing, and Part 2, which is just 5 characteristics that are true of all enzymes. So big ideas, things we're going to talk about. We want to know, one, why are we talking about enzymes in biology? What is their significance in terms of us studying life? What are they? How do they work? And how, or what things rather, can impact their function or how well they operate? We start with this right here. And you guys have actually already seen this. When we did our building activity, you looked at one of these. This is an energy reaction graph. So if we look on my x-axis, make that thing go away, we have progress of reaction. So as I move this direction towards the positive x, my reaction time is passing, my reaction's going on. And as I look at my y-axis, I have energy. So as I move in the positive y direction, I have more and more energy. The line of this graph is telling me I'm going to start with something that has some amount of energy in it. I'm going to add a lot more energy in until I reach a tippity top peak where I've got this nice star. And then energy is going to start to be released, and it's going to release and release and release until we reach some bottom thing down here. What we're going to do right now is actually fill this in. So this line right here represents what I start a chemical reaction in. And these things contain some energy within them, which is why this is a positive Y value. They have some energy already in them. And we call these things that go into a chemical reaction. I'm sure you know them. Those are your reactants. So you'll notice that reactants is a general term we learned early in this year for anything that goes into a chemical reaction. I added something in underneath here because we're actually going to learn a new term in this unit. When we are talking about enzymes, so something an enzyme is going to work on, then we call it a substrate. So when we hear the word substrate, don't get hung up. It literally just means reactant or thing going into a chemical reaction, but we know we're kind of in the enzymes unit. So we're using our enzyme specific term for this instead of our general umbrella term reactant for anything that goes in. I then notice, so if reactants are my stuff going in, my other green line all the way down here, this is going to be the stuff I make. Those are my products. So reactants in, products out. But in order to convert something into something else, we notice we have to do this whole energy bump right here. We have to add a bunch of energy in till I reach this point, and then energy is going to be released. So C is pointing to this hill right here, this energy hill we have to overcome to convert reactants into products. And that hill has a name. It's called the activation energy. So to activate means to turn on or start. So activation energy is literally the energy to start a chemical reaction. Unless I put, see this arrow right here, unless I put all this energy into my reactants, well, then they don't turn into products. We don't get a chemical reaction going on. And we notice we've got this nice little fancy star point right here. Let's give that a name. So we know that the way this reaction is going to work is I have reactants, they have some energy in them, but I need to break them all apart. So I add energy, add energy, add energy, add energy, add energy, until eventually I've added enough energy in that my reactants fall separated one another. So atoms are no longer connected to each other. They're all broken apart and separated, ready to be reformed into something new. That point where they're all broken apart, that's your transition state. So it's where we don't have reactants anymore. We're kind of back to raw ingredients. We're ready to make something new. And then we're going to give our definition. We already kind of talked about it, but let's formalize it in our notes. So if you look right now, your part 1, pause right here if you need to, should look like mine, where you've got your graph labeled with all of these terms, and then you've used that right-hand side where I gave you some space to actually define what is transition state and what is activation energy. We're going to talk a little bit about why enzymes are important and some characteristics of enzymes. So for you to be alive, so for you to sit there, listen to this video, pick up a pencil, it requires thousands and thousands of chemical reactions to occur all the time. If you had to wait for all of these chemical reactions to occur on their own, so to absorb enough energy in the reactants that they convert to products, you would be waiting a very long time. So long that we would not get life the way we have it now. So that's why what enzymes are going to do is they're going to lower this activation energy. So the amount of energy I have to put in to convert reactants into products. And when they do that, it allows me to perform all of these essential life-saving reactions very, very quickly and sustain life. So without them, we wouldn't be able to have life-sustaining reactions occur fast enough to keep us alive. Oh, and we kind of talked about this. So we're talking about how waiting for reactions to happen on their own is not a viable way to do this. So enzymes are going to help to speed that up. So we're going to quickly go through 5 things that are true about all enzymes. So number 1, all enzymes are proteins. So this is their classification in terms of organic molecules. So pause the video here, take a minute or two, and in that space underneath, brainstorm. Because they are proteins, what can you tell me about them? So what elements do you know have to be in them? What is their building block? What do we make when we put them together? What holds them together? Basically draw on your past unit and now apply it to something. So apply it to this new unit. So pause here. The next thing we need to know about enzymes is how they're named. So naming enzymes is really simple. They all end in ACE, A-S-E, not to be confused with OSE, O-S-E, which is what we find in our carbohydrates. And they typically begin with what they break down. So pause here again. You've got these 6 examples of enzymes. Hit pause on the video and see if you can figure out, using this idea that the root, so for example, cellulase, comes from what molecule it's breaking down, and then ACE tells me it's an enzyme. So see if you can go through these 6 and figure out, what do they go with? Are they breaking down? So hopefully we paused and we were able to do this. So cellulase breaks down cellulose. Maltase is going to break down maltose. Protease breaks down proteins. Nucleases, this one's a little tricky because you might have thought nucleic acids, but it's actually nucleotides. If you put nucleic acids, you're applying the idea, right? It's just kind of a tricky one. Sucrase breaks down sucrose, and lipase breaks down lipids. Okay, so we get the naming conventions of enzymes. Take what it breaks down, add ACE on the end. We know it's an enzyme, and we know what it's breaking down. So we talked about how enzymes speed up chemical reactions by lowering activation energy. What I would like you guys to do right now is add activation energy. So get this in your notes. This is something that's true of all enzymes. It's one of our 5 things that's true of any enzyme in nature. And then I want you to try with your table the people around you. These are 2 graphs. I want you to go back to your first page, and I want you to find where on these graphs do we see activation energy. And then I want you to make a prediction. How is this graph going to change if we were to lower activation energy? So I'm going to give you a couple hints here. 1, lowering activation energy means that we are going to make reactions happen faster, but I changed nothing about my reactants and products. So we shouldn't be altering any part of this graph when it comes to reactants and products. So pause here again with the people around you. Take your best guess. We're going to go over this and see if you can figure out, how would this graph change if we were to use an enzyme? How would it change the shape of the graph? Ooh, we'll do this one together, so I'm going to skip it for right now. The 4th thing we want to know about enzymes is that enzymes are substrate specific. So substrates are the molecules that an enzyme works on. So that means each enzyme has to be perfectly shaped in order to work on one molecule. So for example, sucrase only works on sucrose. It doesn't work on maltose. It doesn't work on cellulose. It doesn't work on lipids or proteins. It is perfectly shaped to break down that one molecule, which is why every molecule inside of us has its own specific enzyme, because they're specific. They only work on one. And the last thing we want to know about all enzymes is that they are reusable. They help reactions to occur faster, but they are not a part of the reaction themselves. They don't change in any way, shape, or form. So when an enzyme helps reactant to convert to product quickly, as soon as it's done with that reaction, it literally goes and finds another reactant and starts all over again. They get used over and over and over again inside of us because they're not a part of the reaction. They're just a helper within that reaction. So you should have all of parts 1 and 2 done. There is a second video, but go back through if you're missing anything, or if you need to go back and pause and kind of work on those sections that I gave you for 5 characteristics of enzymes. Please do that now.